What I want to do in this video is to provide ourselves with a rigorous definition of what it means to take the limit of a sequence as n approaches infinity. And what we'll see is it's actually very similar to the definition of any function, taking any function as the limit approaches infinity. And this is because these sequences really can be just viewed as a function of their indices. So let's say, let me draw an arbitrary sequence right over here. So actually, let me draw it like this, just to make it clear what the limit is approaching. So let me draw a sequence. Let me draw a sequence that is jumping around a little bit. So let's say when n is equal to 1, a sub 1 is there. When n is equal to 2, a sub 2 is there. When n is equal to 3, a sub 3 is over there. When n is equal to 4, a sub 4 is over here. When n is equal to 5, a sub 5 is over here. And it looks like as n is, so this is 1, 2, 3, 4, 5. And so it looks like as n gets bigger and bigger and bigger, a sub n seems to be approaching some value. It seems to be getting closer and closer. It seems to be converging to some value L right over here. But what we need to do is come up with a definition of what does it really mean to converge to L. So let's say for any, so we're going to say that you converge to L if for any epsilon greater than 0, for any positive epsilon, you can come up, you can get, or you can, there is, or maybe I'll write it this way. For any positive epsilon, there is a positive m, capital M, such that if lowercase n is greater than capital M, then the distance between a sub n, and our limit, this L right over here, the distance between those 2 points is less than epsilon. If you can do this for any epsilon greater than 0, there's a positive m such that if n is greater than m, then the distance between a sub n and our limit is less than epsilon, then we can say that the limit of a sub n as n approaches infinity is equal to L, and we can say that a sub n converges to L. So let's parse this. So here I was making the claim that that a sub n is approaching this L right over here. I tried to draw it as a horizontal line. This definition of what it means to converge, for a sequence to converge, says, look, for any epsilon greater than 0. So let me pick an epsilon greater than 0. So I'm going to go to L plus epsilon. Actually, let me do it right over here. L, let's say this is L plus epsilon, and let's say this is right here. This is L minus epsilon. L minus epsilon. So let me draw those two bounds right over here. And so I picked an epsilon here. So for any arbitrary positive epsilon I pick, we can find a positive m. So that as long as, so let's say that is our m right over there. So that as long as our n is greater than our m, then our a sub n is within epsilon of L. So being within epsilon of L is essentially being in this range. This right over here is just saying, look, the distance between a sub n and L is less than epsilon. So that would be any of these. Anything that's in this between L minus epsilon and L plus epsilon, the distance between that and our limit is going to be less than epsilon. And we see right over here, at least visually, if we pick m there, if you take an n that's larger than that m, if you pick an n that's larger than m, if n is equal to 3, a sub n seems to be close enough. If n is 4, a sub n is even getting closer. It's within our epsilon. So if we can say this is true for any epsilon that we pick, then we can say that the limit exists, that a sub n converges to L. In the next video, we'll use this definition to actually prove that a sequence converges.